So hello everyone. Uh, Now we would be starting with the first week of the linear dynamical system course. So in the first week we would be discussing about the state space solution, realization and its equivalence. So this is the outline of the first week where we would be starting with the brief introduction about the input output description. Later on we would also introduce the notion of the states. Then we would proceed with the solution of the state space system, particularly for the linear systems. And this linear systems, we would be dealing both in the time variant case and in the time invariant case. The third module deals with the equivalent representation of the linear systems. And in the third and the final one, we introduce the realization problem and its solution. So to proceed with the definition of the dynamical system. So how do we define a dynamical system? In the sense that a dynamical system basically interacts with its environment through the input output variables. So here the input variable is defined by the u of t, while the output of the dynamical system is defined by the y of t. Now note here that whenever we are discussing about the continuous time system, we use this representation where u of t of any signal. So if we are in the continuous time, we would be denoting all the variables. Let's say the variable is z. So this variable, if I denote like this, it means that the system is in the continuous time. Now if we are discussing about the discrete time, either we would be using the same notion z of t, but with the specific definition of the t that it belongs to the integer, or z of k. So here k is implicit that it belongs to the set of integers. Okay. So the first important property of a dynamical system is the causality. The causality is defined that in the sense if the current output depends on past and current inputs but not on the future inputs, then we say that the system is causal. This causality is basically a necessary condition for any system to be built or physically implementable in the real world. So here two aspects are introduced. That first is the current output either depend on the past input or on the current input. So one of the most important property of the dynamical system is the causality. We define the causality in the sense that if the current output depends on the past and current inputs but not on the future system, not on the future inputs, we say that the system is causal. Now causality is basically a necessary condition for any system to be built or physically implementable or realizable in the real world. Now there are two aspects here, that the current output either depends on the past input or on the current input. Here we would introduce two notions, that if the current output depends only on the current inputs, then we say those systems are the memoryless systems. Now if the current output depends on the past inputs, so how far, the question arises that how far back in time will the past input affects the current output? The answer to this question is that we need the entire history of the input starting from minus infinity up to the current time t to actually compute the output y at time t. Now this representation we would be using a number of times. This means that the u of t is applied to a dynamical system which yields the output y of t. Now here it says that we need to compute the output at time t, we need the information of the control input starting from minus infinity up to time t. Now the problem arises here is that tracking ut from t is equal to minus infinity is very inconvenient. So how we can address this problem? To address this problem, we would introduce the notion of the state, so that instead of tracking the entire history of the u starting from minus infinity, is there any answer that, or is there any time from which we need to know the control input to actually compute the output at time t? So in this respect, the state of a system at time t naught, that is x of t naught, is the information at t naught that together with the input u of t for t greater than equal to t naught determines uniquely the output y of t. What does it mean? That now if we have the information about the state at time t naught, then we do not need to know the ut applied before t naught. So in fact the state summarizes the effect of the past input on the future output. Say for example, consider this electrical circuit. Now if we know the voltages x1 of t naught, x2 of t naught across the two capacitors and the current x3 of t naught passing through the inductor, then for any input applied on and after t naught, we can determine uniquely the output for t greater than or equal to t naught. So if we have three states in the previous example, we define a state variable as a vector of three state variables x1, x2, x3, and this x is basically of dimension 3. Now if we revisit the input output description of the system we introduced earlier by using the notion of the state, it says that if we have the information about the state at t naught and we have the information about u starting from that t naught up to time t, then only this information is required to compute uniquely the y of t for all t greater than or equal to t naught. Again, this is a dynamical system to which the input is applied and the output is obtained. Linearity is another important property of dynamical systems. So we say that the system is linear if it satisfies the superposition property. Now this superposition property is basically the combination of two properties. One is the additivity and another is homogeneity. So additivity says that if we apply x1 u1 to any dynamical system S and we obtain the output y, and if we apply x2 and u2 to the same dynamical system which gives us the output y2, then if we take the linear combination of the state and the input, that is to say we define x3 as x1 plus x2 and u3 as u1 plus u2, then if we apply this input to the system S, then the output which we obtained y3 should be y1 plus y2. Now homogeneity says that if we have x1 comma u1 applied to the dynamical system S and we obtain the output y1, now if we take any constant, real constant, let's say alpha, and multiply this x1 and u1 to the same dynamical system, then the output which we obtain, let's say y2, should be equal to alpha of y1. Now we combine these two properties, it gives us this definition. For any real constants alpha 1 and alpha 2, if we take this input input states, or let's say the state vector as x3 and the input signal as u3, then this is the output we would obtain as y3. If the system does not satisfy this property, we say that the system is nonlinear. Now based on the input state output variables, we will define two types of responses. First is the zero input response and second is the zero state response. So as the name suggests, in the zero input response we put u of t is equal to 0 for all t greater than or equal to t naught, and for the zero state response we put the value of the state at time t naught equal to 0, and corresponding to these two responses we denote y of zi, that is the zero input response, and the zero state response. So now if I combine these two responses owing to the superposition property, then the complete output due to xt naught and ut, which we define as the total response of the system, and we take the output due to the zero input, that is yz of I, and the output due to, when we put the state equal to 0, then the total response is basically the summation of yzi and yzs. Now first we will see the zero state response of the system, and later we would combine both the responses into one through the state space representation. Now to proceed with, let's consider the SISO system, that is the single input single output system. Both input output variables are scalar variables. Now we define a pulse function which is of width delta and having a height 1 over delta. So if we take the property of the impulse function, that the area under this pulse should be equal to 1 and it should be 0 other than this width. In the figure B, we considered a time shifted version of this pulse where instead of starting with the t is equal to 0, we are starting with some ti by keeping the same width of delta. But here notice that we put the magnitude equal to 1 instead of 1 by delta. So if we take the area inside this curve, it is now delta. So now if we take any input signal, which is a continuous time signal, and we multiply that signal with this pulse, and we need to know the value of the input signal at time ti, then this input variable is defined by this equation, u of ti into delta of capital delta t minus ti into delta, and we know that this part is equal to 1, right? So we can approximate the input signal u of t by the summation of this value over all the i's, right? So this is expressed by this equation. Now suppose we define g of capital delta t comma ti as the output of the system at time ti, which is excited by the pulse ut applied at time ti. So pay attention to these two variables t comma ti. So it says that we are applying the input at ti and we are obtaining and we are observing the output at time t. Okay, so this can be represented by using our earlier notation, that when the input delta of capital delta is applied to the dynamical system, we obtain this response. Now if I multiply this input by u of ti and capital delta, so seeing the homogeneity property, the output should also be multiplied with this two variables. Now introducing the additivity property, if I sum them up over all the i's, we obtain an approximate output of the system which is defined by this summation of this entire quantity. So still let's pay a bit of attention to this equation. This equation is still an approximation of the output of the dynamical system. Now if we want to have the equality, so there are certain things which we need to take care of. Say suppose if the capital delta approaches to 0, then we know that the pulse we introduce in fact would become an impulse function. So we remove this capital delta and we represent this by a shifted version of the impulse function, and the corresponding output will be denoted by g t comma ti. We also remove the capital delta from the subscript. Further exploring the properties of the capital delta approaching towards to 0, that this capital delta can be written as d tau, a small width. Now all the discrete time instants ti would become a continuous and can be replaced by variable tau. This summation would become an integral, and this approximation in that case would become an equality. So basically this concept is obtained from the Riemann integral owing to this equation which defines the Riemann integral. So now y of t is defined by an integral from minus infinity to infinity, g of t comma tau u tau d tau. Now it says that the input was applied at time t is equal to tau and we are obtaining the output at time t. Okay, and this g function is now defined as the impulse response of the system. Now if we apply the causality property on the impulse response of the system, we know that the output cannot appear before the input is applied. So in that case, causality implies, or it's equivalent to gt comma tau is equal to 0 for all t greater than less than tau, right? So if we apply this into the last equation, now we start from t naught up to time t, and the rest quantity would remain similar. So instead of this minus infinity to infinity, we would have from t0 to t. So up to this point, we have not introduced the notion of time variant and time invariant. So the input output description of the system given by this equation is in fact valid for both types of systems. Okay, we will further distinguish that how to do the analysis for the time invariant case and for the time varying case. So we have this first result of the impulse response, that consider a continuous time linear system with m number of inputs and p number of outputs. There exists a matrix valued signal capital G t comma tau, which is basically a matrix of dimension p cross m. Now note that here that whenever we are defining any function, we will be using the small letters. Now if we are defining the relationship between the input and output by a function with a capital letter, it means that we are implicitly considering that that function is a matrix. So such that for every input u, now here u is also a vector, a corresponding output is given by y of t, which is given by this equation. Here u and y both are vector signals. So now if we impose the time invariant property, that if we shift the arguments of the function t comma tau by some constant capital T, then the behavior of the system should not change. So this first equation basically says that g t comma tau should be equal to gt plus t comma t plus capital tau plus capital T. Now if, since the system is time invariant, this third equality is also satisfied. Now with the slight abuse of notation, we have used the same notation of the variable capital G by removing the second argument, because the second argument is basically 0. So we can define the capital G as t comma tau for any capital T. So the important point to note here is that when we are dealing with the time invariant system, in that case we do not need two different arguments of the function capital G. So assuming that t0 is, now we are starting with the t0 is equal to 0, we define the output y of t by this equation, and the second equation is basically denotes the convolution between the capital G and the input signal u for all time t greater than or equal to 0, and this star denotes the convolution operator. So both of the representation are valid, we can use either of them. Now going towards the discrete time system, the similar theorem applies in the discrete time system as well, that if the considered a dynamic discrete time linear system with m inputs and p outputs, there exists a matrix valued function g t comma tau of having the dimension p cross m, such that for every input u, a corresponding output is given by y of t. Now here you would notice that since we are dealing with the discrete time system, we are having the summation from t0 to capital T, and we define both t and tau, both are integers. Okay. Now if the system is time invariant as well, then the time shifting property holds, as we had seen in the earlier slide, and assuming t0 is equal to 0, this is the response of the system when we assume the state is equal to 0. Okay. Now here we see two versions, in fact two equations of computing the output of the system in the continuous time domain and the discrete time domain. In both the representations, we need to solve either the summation or the integral, which might be a bit time consuming. So in order to obtain the response of the system, we deal in the frequency domain. So let's see that what is the equivalence between the time domain representation and the frequency domain representation. So let's see the first equation, which is the basic equation what we had seen from the previous result. Now if I take the Laplace transform of this part, we denote y hat of s. So whenever we are using the frequency domain transformation of any time domain signal, we will introduce a hat over the same variable, which is similar to what has been done here, y hat of s. So if we take this integral 0 to infinity and 0 to infinity of this one, and this is given by e to the power minus st gt comma minus tau u tau d tau and dt. So if I write explicitly, we would have y hat of s in by 0 to infinity y of t e to the power minus st dt. So we just put yt from here to here, and then we obtain basically this one. Okay. Now if we change the order of the integration and rearrange the integrals by changing the order of the integration, is we will put this order of integration, we interchange this d tau and dt. So we club these terms e to the power minus st minus tau. So here in the above equation we had e to the power minus st. Since we have introduced e to the power s tau here, we need to cancel it out by e to the power minus s tau. Okay, so we club these two terms by this one, and these two terms are clubbed into one. Now if we see or if we pay a bit of close attention to the inner integral, that this defines basically the Laplace transform. But before the Laplace transform, we need to see that how the causality property is playing its role to finally say that it is the Laplace transform. So but because of the causality, let's see, we have the same integral here. Now if we, in this equation, if we replace t minus tau by another variable t bar, right? Now this dt, if we take the derivative of this one, it would be dt. Since tau is not a function of capital T, it would be 0, and here we would be having dt bar. So dt would be replaced by dt bar, and t minus tau is replaced by t bar. So this t minus tau is t bar, and this also t bar, and dt is dt bar. This is what written in the second and on the middle in this row. Now if we see the limits, if I put t is equal to 0, if we check the lower limit, if I put t is equal to 0, we would be having minus tau as tau bar, right? And if I put the infinity, it would be infinity. So now this limit from 0 to infinity would change to minus tau to infinity if we are doing this integral over t bar, right? Now since we know that our system is causal, we cannot have this lower limit below 0. So it has to start from 0, otherwise the system would not be causal. So we start with 0 to infinity. So this integral and this integral would now remain the same, and this part can now be written as the Laplace transform of the impulse function, which was defined in the time domain. Now substituting 2 into 1 and removing g hat of s, because this g hat of s should go here. Now notice that we are taking the integral over tau, and g hat of s would become a constant for this integral. So we can take this outside, and the inner integral is basically the Laplace transform of the u hat. So our equation, the final equation, is that y hat of s in the frequency domain is given by the multiplication of the Laplace transform of the impulse function and the Laplace transform of the input signal. So the convolution in the time domain is transformed into merely a multiplication of the two functions. So here we have these two definitions in the continuous time domain and in the discrete time domain, that the transfer function of a continuous time, this is a continuous time, causal linear time invariant system, is the Laplace transform defined by this. Okay, where s is basically a complex number of an impulse response gt2 comma t1, and can be replaced by t2 minus t1, what we had seen in the earlier slides, for all t2 greater than equal to t1 and greater than equal to 0. Similarly, in the discrete time domain, we would be taking the z transform. and the transfer function is defined by g hat of z by this summation n, where t1 and t2 and t is basically the integer and z again is a complex number. So now introducing the state space representation of a linear system. The idea behind introducing the state space representation is that whenever we are defining the output of the system, considering only the inputs and the outputs, then we define the zero state response. Now if we need to compute a unique response combining the state and the output, we need some representation. The earlier description we saw only in terms of the signals x, u and y. So this state space representation we would be using for the linear systems, that we introduce this x, which is our state variable. So by x dot is equal to a of t, x of t plus b of t, u of t. Now the interesting thing of this state space representation is that given any higher order differential equation in terms of u and y, you can parameterize that higher order differential equation into this first order differential equation by introducing the notion of the state x. Okay? So the first equation we call the state equation, the second equation we call the output equation. And note that here that all the dynamics are embedded into the state equation because of this derivative part, and the output equation is basically an algebraic equation because here we do not have any derivative or integrals. So this representation we say is for the time varying system because all these parameters a, b, c, d are the functions of time. Now if all these four parameters are constants, then we define that system as an LTI system. Let's see. So what flexibility does the state space representation offers to us? Now let's say we could have one system or two systems which might be interconnecting. Let's say we have this dynamical system S1. Either there could be an interconnection with another dynamical system S2 in this way, which we define the cascaded one. So if I club them S1 and S2, this would give me the overall system. Another one we could have as a parallel combination of S1 and S2 having the same input. Then we could also write the state space representation of the entire system. Here we would see the feedback system where we define the dynamical system by P1 having an input output variable as z and y, and this y is fed back to the plant P1. Right? Now given this P1, which is basically a mapping from z to y, denoted by this state space representation where we have assumed that A1, B1, C1, D1 all are constants. Now we need to compute the S, which is the mapping from U to Y. So solving this state space representation, we finally obtain this state space representation of the entire system. Now we won't be discussing in detail that how we have obtained these. So you could define that this is A bar, this is B bar, let's say D bar, and C bar. So this you can write in a compact way as x dot is equal to A bar x plus B bar u, and y is equal to C bar x plus D bar u. So note that here that when we have represented the P1, the input is Z1, but the state remains the same, and the output we have the Y1. Okay, so here there is a minor typo. It should be basically Y, because we have denoted by Y here. Now when we compute the mapping from U to Y, the input of the system is replaced by U from Z, and all these matrices are now changed to these matrices by keeping the same output variable and the same state variable. Okay, so this you can show by yourself, that if we have any a feedback system, then how to compute the overall state space representation from U to Y. Now introducing the impulse response and the transfer function for LTI system, what we are basically aiming at to see the relationship between the input output description what we had introduced earlier and the state space system we just introduced now. So consider the continuous time LTI system, which is defined by ABCD matrices. So there are two ways of representing a continuous time LTI system. Either we write these two complete equations, or we write just that the ABCD pair. Okay, so this is also a state space system, and this is also a state space system. Now if we take the Laplace transform of these two equations, we obtain this x hat of s minus x of 0, which is the initial condition. If the initial condition is 0 at time t is equal to 0, then this part would be 0, right? This we would investigate later. And similarly the output equation, because this is merely a algebraic equation. Now if we solve for x of hat of s from this equation, we obtain x hat of s. We have si minus a. If we take this a here, we obtain this si minus a and that inverse bu hat plus si minus a inverse into x naught. Now the next step is to put this x hat of s here, from which we conclude that if I put this x hat of s into the output equation, we obtain this representation, which is y hat of s is equal to psi hat of s x naught plus g hat of s into u hat of s, where phi hat or psi hat and g hat are defined by these two equations. So the interesting point to note here is that if we have x of 0 is equal to 0, so this part would be equal to 0, and we obtain the same equation what we had obtained earlier before introducing the state space representation. Okay, now if we have the u hat of s equal to 0, which implies that the 0 input response, then the only response we are having because of the initial condition x naught. So basically it is a linear combination of the responses due to the initial condition plus the input to the system. So if we go back into the time domain by taking the Laplace inverse, we obtain y of t is equal to psi t x naught plus g convolution with u into t, where we g of t and psi of t are basically the Laplace inverse of g hat and psi hat. So we have our next result in the continuous time domain, that the impulse response and transfer function of the continuous time in the continuous time linear time invariant system, which are given by g of t as the Laplace inverse of ABCD matrices, this combination of ABCD matrices, and g hat of s is given by this respectively. Moreover, the response yt is equal to convolution of gu corresponds to the 0 initial condition what we had seen in the last slide. Okay, now consider the discrete time LTI system, which we are denoting by x plus. By this x plus, we mean to say that xk plus 1 is equal to a xk plus b uk. So here we are using the shorthand notation that xk plus 1 is denoted by x plus. So the important difference between the state space representation of the continuous time system and the discrete time system is that now both the systems have become the algebraic equation, the state equation and the output equation. So in the discrete time domain, the next result speaks the impulse response and transfer function of the discrete LTI system are given by the Z transform of the combination of ABCD matrices, and the G hat of Z is defined by this part. Moreover, the response, the convolution between the G and U, corresponds to the 0 initial condition, which is x0 of z should be equal to 0. Okay. Now here the idea behind introducing the Laplace transform is that instead of computing the convolution or the integral in the continuous time domain and the summation in the discrete time domain, we dealt in the frequency domain by using the transforms, either by using the Laplace or by using the Z transform. So, but we cannot use these two frequency domain tools for the linear time varying systems. Why? First of all, that the Laplace transform of gt comma tau is now a function of two variables. For the LTI system, instead of having these two variables, we use only one argument, which is t minus tau. Right? Now here we would be taking the Laplace transform of which is a function of two variables. And now the second problem is that the Laplace of the multiplication of at into xt is not equal to Laplace of at and Laplace of x. Pay attention to the LTI case when we have this x dot is equal to ax plus bu, where a and b matrices are the constant matrices. Suppose we have the zero initial condition, that is to say x0 is equal to 0. Okay, now if I take the Laplace transform of both sides, then this I could write x hat of s, and this part let's denote for the moment as a into x plus Laplace of b into u. Okay, being a as a constant matrix, I could take it outside, right? Which is not the case here for the time invariant case. So we cannot take the Laplace transform here. Because of these two basic problems, we cannot use this Laplace transform or the Z transform for the LTV case. Okay. So now in the next lecture, we would see how to compute the solution of the LTV system, because for the LTI system, we could use the frequency domain tools, likewise we had seen. So first we will see a pure solution in the time domain for the linear time varying systems, and then we will tailor that solution for the LTI case.